Section 5.6, Graphs of Other Trigonometric Functions. Here's the graph of y equals the tangent of x. Notice that it goes up towards positive infinity and down towards negative infinity. Compare that to the graph of y equals sine x and y equals cosine x that we studied earlier, and you'll recall that those oscillated between 1 and -1, the region that I'm shading now. So let's think about where we get the graph of y equals tangent of x. To begin this graph, we'll substitute some values in for x. Let's start with 0 degrees, 0 radians, and the tangent of 0 is 0. So that gives us this point right here. If we move on to 30 degrees, we can do it approximately as 0.6, and that gives us this point. 45 degrees is up at a height of 1, so that's about here. 60 degrees is approximately 1.7, so that's up about this height. Continuing on, we'll get closer and closer to 90. As we go to 75, the tangent of 75 degrees is 3.7. That's about here. The tangent of 85 degrees is 11.4. On the scale of this graph, it'd be about here. Getting even closer to 90, the tangent of 89 degrees is at a height of 57.3, and that's way off the top of the screen. Moving on to 89.95 degrees, the tangent of that is way off the top of the screen, which brings us to the tangent of 90 degrees. Remember, the tangent of pi over 2 or 90 degrees is undefined. So on our graph, we get this vertical asymptote. We can then draw a curve through these points, and if we go in the negative direction, we get a similar curve and a vertical asymptote at x equals negative pi over 2. Unlike the graphs of y equals sine of x and y equals cosine of x, which need 2 pi to go through a complete cycle, the period of the tangent curve needs pi to go through a complete cycle. From 0 to pi over 2, we get the positive portion of the graph, and from pi over 2 to pi, we get the negative portion of the graph. You'll see that it repeats every pi units. You may notice that you could have one complete segment if you go from pi over 2 to 3 pi over 2, but typically when we're asked to graph one period of the tangent function, we go from 0 to pi. Notice that the domain is going to be all real numbers except where we have the undefineds, and this occurs at odd multiples of pi over 2. And the range is all real numbers because we get everything from negative infinity all the way up to positive infinity. The tangent curve is an odd function, so the tangent of negative x equals the negative tangent of x. There are vertical asymptotes at odd multiples of pi over 2. The points plotted now on the x-axis occur midway between each pair of consecutive asymptotes, so that should help us graph. Additionally, there's going to be points at the 1/4 mark between each asymptote. Those will be at -1, and at the 3/4 mark between each asymptote, that will be up at +1. Now we'll look at the graph of y equals the cotangent of x. It's similar to the tangent. Note that instead of going up from left to right, the curves come down from left to right. The period is pi. The domain is all real numbers except for multiples of pi, and the range is all real numbers. The cotangent curve has vertical asymptotes at multiples of pi. It has x-intercepts midway between each pair of consecutive asymptotes. It's an odd function. 1/4 of the way between consecutive asymptotes, the graph will be up at +1, and 3/4 of the way it will be down at -1. So now that we've graphed 4 of the trig functions, the 2 that are remaining can be obtained by considering their reciprocal identities. Cosecant is 1 over sine, and secant is 1 over cosine. We will obtain values on the graph of the cosecant of x by finding values on the graph of the sine of x. Recall the graph of y equals sine of x has these 5 key values. At 0, it's at a height of 0. At 90 degrees or pi over 2, it's at a height of 1. It comes back down to 0 at pi or 180. At 270 degrees, it's at -1. And then at 2 pi or 360, it's back up to 0. So here's our graph of y equals the cosecant of x. Let's focus in on this portion right here. You'll notice the dotted line is our sine wave. Let me open the window just a little bit so we can see some of these key values. There's our sine wave, starting at 0, going up to a height of 1, coming back down, down to -1, and then finishing a cycle at 2 pi. So notice that anywhere that the sine has a value of 0, then the cosecant is the reciprocal of 0, which is not possible because that's undefined. So the cosecant graph will have asymptotes at each of those locations. And then when the sine is up at 1, the reciprocal of 1 is 1. So the cosecant graph will have that same point. And at -1, the reciprocal of -1 is also -1, so the cosecant curve will have that point. Then we draw a U shape going up and down through those points towards the asymptotes. And that gives us our curve. Notice that the dashed line used to draw the sine wave is not part of the cosecant curve. It's just like scaffolding that helps us get it graphed. So let's take a closer look at this point right here. The reciprocal of 1 is 1, so that's why that point is also on the cosecant. Notice as we came down a little bit in this direction for the sine value, if let's say we were at 9/10, 9 over 10, the reciprocal of that would be 10 over 9, which is about 1.1. So you go from being slightly below the line to slightly above the line. As you proceed closer and closer to a height of 0, why does the cosecant graph rise so rapidly? One way to think about it is as we proceed closer to this 0, 0, at some point we will be a fraction of 1/1000th above the x-axis. And therefore the cosecant would be the reciprocal of that, 1,000 over 1. So it's going to be up at a height of 1,000. And again, you can keep getting closer and closer. 1 over a million would be up at a million. So that's why this has this feature. When you have the portion of the sine wave that's negative, their reciprocals will be negative, and so therefore a very small negative number is way down on our graph in the negative direction. Some of its characteristics include having vertical asymptotes at multiples of pi. It's an odd function, so the cosecant of -x will equal the minus the cosecant of x. The cosecant of x has a period of 2 pi. You get the upper portion going from 0 to pi, and you get the lower portion continuing on to 2 pi. The domain is all real numbers except for multiples of pi. This graph continues infinitely in both directions of the x-axis, but anywhere there's an asymptote, you need to exclude it. The range is all real numbers going up and down except those between 1 and -1. So the way we say that is y is less than or equal to -1. That gives us the lower portion, and y is greater than or equal to 1. In interval notation, we write that as the interval going from -infinity to -1, and the bracket around -1 indicates that that point is included. The U is the union symbol, so we combine that with all the points that go from 1, including 1, all the way up to positive infinity. Finally, let's look at y equals the secant of x. Because the secant is reciprocal with the cosine, we will use the cosine graph to find some values. Anytime that the cosine graph is at a height of 1, since the reciprocal of 1 is 1, then the secant graph will have the point at that height. Down at -1, the reciprocal of -1 is -1, so that point will also be on our secant graph. And then anywhere that the cosine is at a height of 0, since that reciprocal is undefined, there'll be an asymptote on the secant graph. So here's the graph of y equals the secant of x. If we look at the dashed cosine graph in between 0 and 2 pi, as we mentioned, anytime it's at a height of 1, we get that point on our secant. Anytime it's at a height of -1, we'll get a u that's going down from that point. And anywhere that there was a 0 on the cosine curve, we get an asymptote on the secant curve. The secant curve has vertical asymptotes. Those come at odd multiples of pi over 2. And it's an even function, which means as you go in the negative direction, those x values will give you the same height as if you go in the positive direction. The secant graph has a period of 2 pi. Its domain is going to be all real numbers except at odd multiples of pi over 2. The range is similar to that of the cosecant, and that is that it goes from -infinity and stops at -1, and then picks back up at 1 and goes up to positive infinity. We have seen that to graph y equals sine x and y equals cosine x, it's helpful to memorize the 5 key values for each. For sine of x, At 0 degrees, it starts out at a height of 0. At 90 degrees, it goes up at 1. At 180, it's back to 0. At 270, down at -1. And at 360, back to 0. We then saw that we could use those 5 key values to help us graph the cosecant by finding their reciprocals. For cosine x, we saw that it starts out at a height of 1 when the angle is 0, down to 0 at 90 degrees. At 180, it's down at -1. At 270, back to 0. And then finally, it finishes the cycle back up at 1. And then we use those points to graph our secant in a similar fashion. But now we want to look at how we can use these values to help us find x-intercepts and asymptotes on the graphs of tangent and cotangent. Specifically, we'll look at the zeros of the sine wave and the cosine wave, and we'll apply that to our tangent graph. First, we need to recall that the tangent has a quotient identity. The tangent of x equals the sine x over the cosine of x. Anytime that the sine is at a height of 0, the numerator of this tangent fraction will be 0, so the tangent will also be 0. So at 0 degrees, 180 degrees, and 360 degrees, the tangent will share these zeros. Furthermore, when the cosine is 0, the denominator of this fraction will be 0, and therefore the tangent will be undefined. If the tangent is undefined, it will have asymptotes at 90 degrees and 270 degrees. We can apply this to the cotangent graph as well. Because cotangent also has a quotient identity, it's the cosine over the sine. So again, anytime that the sine wave is at a height of 0, it's going to zero out this fraction's denominator, and therefore it'll give the cotangent asymptotes on its graph. And finally, when the cosine is 0, the numerator is 0, making the cotangent 0, so it gives us these points at the height of 0 on the graph.